Hello AP Stat students. Here we are making our third and final video for Chapter 9. Again, we're going to continue on with the idea of this thought of a sampling distribution, this big abstract idea. And what we're going to focus in on today is how sampling distributions can help us when we're focused in on means. So, second video we looked at proportions, and again that's an important statistic that we use quite often. And as we've seen many times throughout this class, we'll also use the mean in many situations. So that's what we want to look at next, is the sampling distributions and how they relate to sample means. So the first thing that I want to do is remind you of the process for working with a sampling distribution in general. These were the exact same three steps that we put up yesterday as we dealt with sampling distributions and proportions, and we're going to use the exact same steps today as we work with sampling distributions and how they relate to sample means. So just to review these steps real quick, again, step number one, we need to make sure that a normal distribution is appropriate for us to use. Step number two, we'll find the mean and the standard deviation based on the values of the sampling distribution. And then finally, we'll perform our calculations using the normal distribution. And again, just like yesterday, you have the option of either working with the z-score and your gold packet or your graphing calculator in the normal CDF, whatever your preference is. Again, in today's video, just like video number 2, I will be using the graphing calculator in the normal CDF. So if you have your graphing calculator with you and you want to pull it out so you can follow along, that might not be too bad of an idea. All right. So what we're going to start with is we want to talk about how we check to make sure a normal distribution is appropriate to use when we're working with the means. All right. So let's do that here. So on this slide, I'm showing you the characteristics that we need to make sure are met as we deal with a sample mean. Now remember yesterday with our proportions, we needed to say that the population was 10 times larger than the sample. We needed to say that n times p was greater than or equal to 10, and n times 1 minus p are also greater than or equal to 10. All right? Well, if we think about those characteristics, we're still going to use the characteristic that our population needs to be at least 10 times larger than the sample. So we'll still use that characteristic. That makes sense in this setting, just like it did yesterday. However, we're no longer going to use n times p and n times 1 minus p. Why? Well, we don't have a probability, right? We're not focused on proportions, so why would we deal with a p, all right? Instead, what we're going to look at are some important theorems, all right? First off, if the shape of the population is known to be normal, then the sampling distribution is normal. So what that means for us in practice, if in the problem they tell us the population is normally distributed, we don't have to prove that a normal distribution is appropriate to use. All we need to make sure is that the population is 10 times larger than our sample, and then we're okay to move forward with our normal distribution, okay? However, if they don't tell us that it's normal, or it states that the population is non-normal, all right? What we need to look at next then is the size of our sample, all right? If our sample size is small, and a sample is considered small when our sample size is less than 30, then at this point, with what we know about statistical inference, we won't be able to use a normal distribution, all right? Now, in future chapters, we will talk about how to deal with small samples, but for right now, we're done. That's as far as we could go. All right, we wouldn't be able to complete this problem. Okay. Now, if n is greater than or equal to 30, what we're able to use is something known as the central limit theorem, and we're going to talk about this in just a moment. All right, but the central limit theorem tells us if we have a large sample size, again, n is greater than or equal to 30, then it doesn't matter what the original shape of the population is, its sampling distribution will be normal. All right, and that will be important, okay? Now, let me make this statement as well. Many times in our textbook and as I go through notes, you're going to see the central limit theorem abbreviated as the CLT. All right, so if you see me write down CLT, that's referring to the central limit theorem. And this is going to be a theorem that we use not only here in Chapter 9, but pretty much every chapter that follows after this one. The central limit theorem is very important in statistics. Why? Because again, it gives us the ability to use a normal distribution when the population itself isn't known to be normal. And that's very, very important. All right, that allows us to do a lot more in statistics than we'd be able to do without it. Okay, so let's dive into this idea of the central limit theorem here just a little bit. So this slide formally defines the central limit theorem for us. All right, the central limit theorem says if we draw a simple random sample of size n from any population whatsoever, all right, with a mean of mu and a finite standard deviation of sigma, when n is large, the sampling distribution of the sample mean is close to the normal distribution with a mean of mu and a standard deviation of sigma divided by the square root of n. All right. So what matters to us, again, is from any population whatsoever. It doesn't have to be normal to begin with. It can be extremely skewed. It could be bimodal, whatever the case may be, all right? But as long as n is large, okay, and again, we're going to define n as large as n is greater than or equal to 30, okay? So as long as n is large, what that tells us is that the sampling distribution is close to the normal distribution. And that's important, all right? That, again, is critical as we move forward. So again, if n is large, all right, the sampling distribution of the sample mean is close to the normal distribution, all right? That's what we want to take away from the central limit theorem. Now, if you take a look at the pictures that I have underneath this box, all right, what you see, again, here's our population distribution, okay? Is this first graph. We'll call it graph A. So if I look at this first graph, right, how would you describe that? Okay? Well, obviously we would describe that as extremely right skewed. Okay? Now, the one that we see here underneath the graph, this is representing the center of this distribution, or the mean. Okay? And again, this is a right skewed graph. Right? Now, this is the distribution of our population, but what happens is we begin to take samples from this population and combine them together. Okay, so think about our Post-it note example that we did in class the other day. All right, if we took samples of size 2, all right, well, this is what the shape of that distribution we begin to approach as we look in B. Now, when I look at picture B, this is still very much right skewed. Okay? Again, the center is still at 1, but notice that that graph is starting to shift towards that center. Okay? So look at graph C now, right? In graph C, we've increased our sample size to 10. Right? Now notice how much that shape of the distribution has changed by going from, basically in a population distribution, we have a sample size of 1. All right, we're dealing with each data individually. All right, and again, we had a very right skewed distribution. But as we continue to increase that sample size, that distribution is becoming more and more normal. Now, in graph C here, we would still describe this as right skewed. Right, our right tail here is still longer than our left tail. So we have that right skew. Again, the center is 1, or the mean is at 1, and we can see the peak starting to approach that number. All right, in our final graph, we have n equal to 25. We have a sample size of 25. Okay. Now again, our center is 1. If I look at this, again, this isn't perfectly centered on 1 yet, and we still have a little bit more right skew here in this graph. But as our sample size increases, what it does to that population distribution in creating the sampling distribution is it eliminates the skew. And as you look at the transformation of this graph from A to B to C to D, what you see is that distribution becoming more and more normal. And that's the power of the central limit theorem. All right? So that's why we can use that to justify applying a normal distribution in a non-normal setting. So once we've verified that the normal distribution is appropriate to use, well, what we need next is we need the mean and the standard deviation. Well, the mean and standard deviation formulas were actually given to us within the central limit theorem, but let's define them now, all right? So the mean of the sampling distribution is just simply mu, right? And again, remember, mu is the population mean, right? So that's not going to change. Right? And the standard deviation, well, we know that sampling distributions, their standard deviation gets a lot smaller, right? Well, it's proportional to the square root of the sample size. So the standard deviation of our sample means is the population standard deviation divided by the square root of n. So the larger our sample size, the less variable the data becomes, right? Meaning the more centered it's going to be on the mean, and that's important, all right? Now, the next 2 bullet points are just simple little facts to keep in mind, but the sample mean is an unbiased estimator. Remember, we said something is unbiased if the sample mean is equal to the true mean. Well, that's what we see in our statement up above here, okay? That's what makes it unbiased, all right? And then our bullet point is describing the standard deviation. The values of the sample mean are less spread out for smaller samples, or for larger samples. So again, the larger the sample size, the smaller the standard deviation. So this bullet point kind of explains that. If you want to cut the standard deviation in half, well, you need a sample size 4 times as large. Why? Well, because I'm going to take the square root of that sample size, okay? And so, again, that's the sampling distribution at work. As we increase our data in terms of samples, that standard deviation continues to decrease, and that's an important fact that we want to keep in mind throughout Chapter 9 here. All right? So let's take this information and let's work an actual example problem. So in this example, again, we're going to talk about the heights of young women. We dealt with this the other day in our post-it note example, but we know that that follows a normal distribution. All right? Now here's the good news. Once they tell us that it follows a normal distribution, I'm free to use a normal distribution. I don't have to verify anything, all right? So, again, we stated the other day that the heights of women follow normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. So, part A says, what is the probability that a randomly selected young woman is taller than 66.5 inches? Okay? Now, notice something here first off, all right? How many women am I selecting in this problem? Well, I'm just selecting one, right? What is the probability that a randomly selected young woman is taller than 66.5 inches, right? So this is just a regular old normal distribution problem. So if I draw my normal distribution here, I have a mean in the center of 64.5. And we want to find the probability that somebody is greater than 66.5. So we're looking along at a normal distribution that looks like this. Again, I want you to get in the habit of drawing out your normal distributions. That's going to help us out as we work through statistical inference, okay? So once I have that drawn, all right, now I can use my normal CDF. So this will be the normal CDF. My lower bound would be 66.5. My upper bound is 1E99 since I'm shaded all the way to the right. My mean is 64.5. And my standard deviation is 2.5. And so as I calculate that, my probability comes out to be 0.2116. So I have about a 20% chance, about 1 in 5, of selecting a woman that's taller than 66.5 inches. Okay? Now let's move on to question B. Question B says, what is the probability that the mean of a simple random sample of 10 young women is greater than 66.5 inches? So what's changed in problem B compared to part A is now I'm dealing with a sample of young women, okay? But again, I still want them to be greater than 66.5 inches. So this picture that we drew up in part A, that still applies. It's the same thing. But what's going to change in this problem? Well, again, with what we've learned about sampling distributions, the mean's going to stay the same. The normal distribution picture is going to stay the same. The only thing that's going to change is the standard deviation. All right? So we need to calculate the standard deviation of the sample means, which we know the formula for that is just our standard deviation divided by the square root of our sample size, which would come out to be 0.79. All right, and this is what I'm going to replace in my normal CDF command. All right, so in this problem, working with a sampling distribution, we get a normal CDF of, again, lower bound 66.5, upper bound 1E99 since I'm shaded to the right. The mean is still 64.5, And my standard deviation, this has become much less variable, right, is now 0.79. Now, before we calculate this probability, what do you think is going to happen to the probability? All right, are we more likely to find a group of 10 women with an average height of 66.5 or of a single woman with a height of 66.5? Well, hopefully you answered we're more likely to find a single woman with a height of 66.5. Because again, we know in the normal distribution, or in a sampling distribution, that as our sample size increases, it gets less variable, gets more condensed around the mean, and that's what's happening here. So our probability in this one comes out to be 0.0057. You can see that probability has changed significantly. And again, we shouldn't be surprised by that because of what we know about the sampling distribution. That data, again, is getting less variable, and it's centering itself closer to the mean. All right? So as we deal with a larger sample, it's harder to find a value that's further from the mean. Okay? So let's take a look at one more example. This problem we had where it was known that it's normal. So what do we do if we don't know that it's normal? So here's our second example. It says your company has a contract to maintain 70 air conditioners in an apartment building. The technician requires an average of 1 hour to perform preventative maintenance on an air conditioning unit with a standard deviation of 1 hour. You must schedule a technician's time for a visit to this building. Is it safe to budget an average of 1.1 hours for each unit, or should you budget an average of 1.25 hours? All right? Now, the first thing that we need to notice in this problem is nowhere in the problem did it tell us that this distribution is normal. And it's not safe for us to just automatically assume that it is. All right? What we first need to do is verify that it's normal. And the good news is, all right, our sample size here is 70. Right? What do we notice about the number 70? Well, hopefully we notice that 70 would be considered large. Right? And because 70 is large, all right, we're allowed to use the normal distribution based on the central limit theorem. Right? Because again, our sample size is large, and the central limit theorem told us it doesn't matter what the distribution looks like as long as our sample size is large, which again is greater than or equal to 30, we're safe to apply a normal distribution. All right? So in this problem, again, we're safe to move forward. Okay? So if we take a look at what we're looking at here, all right, we have a normal distribution with a mean of 1 hour. And we want to know if it's safe to budget an average of 1.1. So what we want to find out is what's the probability that it's going to take our technician longer than 1.1 hours to service each of these 70 air conditioners. Okay? And so, again, if we want to apply the normal distribution, well, before we can set that up in our normal CDF, the first thing we need is our standard deviation. Well, again, we know the standard deviation of our sample mean is equal to our standard deviation, which in this problem is 1, divided by the square root of our sample size, which was 70. So our standard deviation comes out to be 0.12. So there's our standard deviation, all right? And now we're ready to find our shaded region, just using, again, a normal CDF, all right? So if we use our normal CDF, sorry there, I experienced some technical difficulties. All right, so our lower limit is 1.1. Our upper limit is 1E99. Our mean is 1, and our standard deviation is 0.12. Right, so if we calculate this probability, right, we're going to end up with a probability of 0.2023. So what this means is there's basically a 20% chance that it's going to take our technician more than 1.1 hour to service an air conditioner. Now, if we're looking at a contract, is that a number that we're safe, that we're comfortable with? Probably not. Not if we're dealing with 70 air conditioning units and 1 in 5 of them is going to take it more than 1.1. right? We're probably not going to have customers real happy when we get behind schedule pretty early, all right? So let's look at 1.25, all right? Now, what do we expect this probability to happen to this probability, okay? Well, hopefully what you say is we expect this probability to go down, all right? Because again, of the small variability that we have within this problem, if I move out to 1.25, right, that's a lot further from my mean. We're now more than 2 standard deviations away. So let's calculate out that probability. So normal CDF, if we budget 1.25 hours, so we're just changing our lower bound now. Everything else is going to stay the same, including our mean and our standard deviation. We haven't changed our sample size at all. Right? This probability comes out to be 0.0186. All right? So we're probably a lot safer with that probability. All right? Only 2% of our air conditioners are going to take more than 1.25 hours. So that's probably a lot better budget of our time. Probably going to keep our customers happy. So we're going to recommend that they budget 1.25 hours based on our data. All right. So there's 2 examples of working with the sampling distribution and how it relates to a sample mean. So again, I hope you see how easy our work is here, basing everything off of the normal distribution. We just need to verify that a normal distribution is appropriate first. From there, we calculate our mean and standard deviation, work with our normal CDF, and we're good to go. All right, so as always, please remember to complete the form below the video, and we'll see you guys soon. Have a great day.
Made with Doodlecast Pro.